Load training data. The training dataset contains 13,700 phase-coded waveforms. The phase-coded waveform object is used to create these pulse waveforms. The waveforms in this dataset are synthetically generated with the following phase code types: Frank, P1, P2, P3, P4, and Zadorfchu. The Zadorfchu waveform sequence index is randomly varied between 1, 5, and 7. Each waveform is of length 256 and the sample rate 1 MHz. The waveforms in the training dataset are distributed across the different code types randomly. This was done to ensure a broad representation of all phase codes in the dataset. To introduce some variability and to create a more realistic training set, noise is randomly added to the phase of each code element of each sample. The noise added is within a range of pi/8 to pi/8 radians. This approach retains the unit envelope while providing slight variability in the training data. Download the phase code pulse waveforms dataset and unzip the data and license file into the current working directory by using the below code snippet. Then next, the training set consists of the noise structure. This is composed of waveforms with noise added for the deep learning network to train. PRF is the pulse repetition frequency. The ratio of the sample rate and PRF must be an integer. The parameters of the signal are defined below. Define discriminator network. Define the discriminator network architecture, which distinguishes between training and generated ambiguity functions of waveforms. The ambiguity function of a signal will be of size m by n, where m is the number of Doppler frequencies and n is the number of time delays. For a signal of length num chips, the delay vector consists of n equals 2 num chips, 1 sample, and the Doppler frequency vector consists of m equals samples. This network takes 512 by 511 by 1 signals as input in the SSC, spatial channel format, which is the size of the ambiguity function of a waveform with sample length 256. Processes the input through a series of 2D convolutional layers with varying numbers of filters. Each convolutional layer uses a kernel size of 6 by 6 with a stride of 2 by 2 and padding of 2 on all sides to maintain the spatial dimensions after convolution. Flattens the output of the last convolutional layer to prepare the data for the final classification layer. Concludes with a fully connected layer that outputs a 1 by 1 by 1 array, representing the scalar prediction score indicating whether the input signal is training data or generated. Discriminator network code snippet is as shown here. These is having CNN network layers and its attributes. CNN network flow diagram is given as shown here. To train the network with a custom training loop and enable automatic differentiation, create a DL network object as shown below. Then initialize learnable and state parameters of the network as shown here. Define generator network. Define the generator network architecture, which generates signals of length 2 by 256 from 1 by 1 by 128 arrays of random values in the SSC, spatial channel format. The first row of the generated matrix represents the real component, while the second row represents the imaginary component of a complex-valued waveform. This network uses a fully connected layer to project the input noise to a higher dimensional space, resulting in an output of 64 by 64 features. Projects and reshapes the arrays to 2 by 8 by 1024 arrays by a custom layer. Upsamples the reshaped array to a larger spatial size using a series of 2D transpose convolutional layers. Each layer uses a kernel size of 5 by 5 and a stride of a 1-2 with same cropping to maintain the spatial dimensions after convolution. Normalizes the output of the final transpose convolutional layer using a custom function layer that applies an L2 normalization function, ensuring the output signal has a unit norm. To project and reshape the noise input, use the custom layer project and reshape layer attached to this example as a supporting file. The project and reshape layer object upscales the input using a fully connected layer and reshapes the output to the specified size. Generator network code snippet is as shown here. These is having CNN network layers and its parameters. CNN network flow diagram is given as shown here. To train the network with a custom training loop and enable automatic differentiation, create a DL network object as shown below. Then initialize learnable and state parameters of the network as shown here. Define model loss functions. Use the helper functions helper model loss D and helper model loss G attached in the helper functions section of the example. This calculates the gradients of the discriminator and generator loss with respect to the learnable parameters of the discriminator and generator networks, respectively. The function helper model loss D takes as input generator and discriminator networks, mini-batch of input data, array of random noise, lambda for gradient penalty, signal length, pulse repetition frequency, PRF, of signal, and returns the loss and the gradients of the loss with respect to the learnable parameters in the discriminator. The function helper model loss G takes as input generator and discriminator networks, array of random noise, signal length, PRF of signal, and returns the loss and the gradients of the loss with respect to the learnable parameters in the generator. Train model batch. Train the WGAN-GP model using a custom training loop. Loop over the training data and update the network parameters at each iteration. To monitor the training progress, display the generated ambiguity functions and a plot of loss functions of the generator and discriminator networks. For each epoch, loop over mini-batches of data. Use mini-batch queue to process and manage the mini-batches of signals. For each mini-batch, use the custom mini-batch FCN helper read signal files attached to this example to read data from the signal data store appropriately and arrange it into an array for network training. Cast the output data to type double. Train on a GPU if one is available. When the output environment option of mini-batch queue is auto, mini-batch queue converts each output to a GPU array if a GPU is available. Using a GPU requires parallel computing toolbox and a supported GPU device. For information on supported devices, see GPU computing requirements. Specify training options. To train a WGAN-GP model, you must train the discriminator for more iterations than the generator. In other words, for each generator iteration, you must train the discriminator for multiple iterations. Set the tunable training parameters as below. For larger datasets, you might want to train the networks for more iterations. For each generator iteration, typically train the discriminator for more iterations. Here, the discriminator is trained for 4 iterations as specified by num iterations d per g. Lambda controls the magnitude of the gradient penalty added to the discriminator. Common values for lambda are in the range of 0.1 to 10. Optimal value is problem-specific and can be found through different trials. Typically, the discriminator learning rate is lesser in comparison to the generator network, as it is trained for more iterations. Here, the learning rate of the discriminator, learn rate d, is 2 times 10 to the power of -4, and the learning rate of the generator, learn rate g, is 1e power -3. The mini-batch size is set as 16 to enable a faster training process. Specify training options in custom training loop describes the other parameters in more detail. As shown here, for num iterations d per g iterations, train the discriminator only. For each mini-batch, evaluate the discriminator model loss and gradients using dlful and the model loss d function. Update the discriminator network parameters using the atom update function. The atom optimizer was chosen for its efficiency and robustness across a wide range of deep learning tasks with minimal need for hyperparameter tuning. After training the discriminator for num iterations d per g iterations, train the generator on a single mini-batch. Evaluate the generator model loss and gradients using dlful and the model loss g function. Update the generator network parameters using the atom update function. After updating the generator network, plot the losses of the two networks. After every validation frequency generator iterations, display a batch of generated images for a fixed held-out generator input. After passing through the data set, shuffle the mini-batch queue. Training can take some time to run and may require many iterations to output good signals. Helper train GAN, attached to this example, sets the training process described above. To train the network on your computer, set Train Now to True or select the Train Now option in Live Editor. Skip the training process by loading the pre-trained network. The training plot below shows an example of the loss functions across the generator training iterations. The 3 loss functions displayed in the plot are for the deep learning architectures: the generator, discriminator with gradient penalty, and discriminator without gradient penalty. The gradient penalty loss term shows stability in the training process with lower loss values in comparison to no gradient penalty. The loss values slowly converge after 100 iterations of training the generator, showing that the discriminator learns a strong feature representation to identify between training and generated signals ambiguity functions. In turn, The generator can generate waveforms with a similar ambiguity function as the training data. In this video we covered load training data, define discriminator network, define generator network, define model loss functions, train model batch and specify training options topics and further topics we will cover in future videos. Thank you.